Hi class, today we are going to learn about waves. So there are some type of waves that are called electromagnetic waves that we do not need a medium for. They can travel through space. And so light and and radio waves and things like that can travel through space, no problem. But most waves need a medium. That's something that the wave travels through. So for this demonstration, our spring is going to be the medium. And so right now the spring is in its rest position. So when it's in the rest position, nothing is happening at all. Now a wave is a way of transmitting energy across a big distance. And so I am going to put some energy in on this side and it's going to come out over on that side. So first I'm going to send a single disturbance through our medium. Again, the spring is the medium. It's not a large, it's not a small, it's a medium. So I'm going to send a single disturbance through that medium, and I want you to watch it carefully. It goes quickly. So you'll notice that the energy went down and then came back and went down and came back, and every time it got a little smaller in amplitude. So what amplitude is a measure of how much energy is in the wave. And the amplitude is basically how far did the medium move from the rest position. And so on this side, we're going to call this the positive side. On this side, we're going to call it the negative side. So if I send a single disturbance again on the positive side here, notice that when it bounces back to me, it bounces back on the negative side. So it comes back the opposite way. And so if we have a single disturbance that goes on this side, the type of wave that I was making here is called a transverse wave. Transverse waves disturb the medium at right angles to the direction of wave flow. And you say, what? And so what that means is I disturbed the medium by, I took my hand and I moved it here and back here. So I moved my hand this way, but the wave itself moved this way. So I disturb the mediums this way, it moves this way, those are at right angles to each other. So I'm disturbing the medium at right angles to the direction of wave flow. So I send it like that and it bounces back the opposite way. When it bounces back, we call that a reflection. Since it bounced back the opposite way like that, it's called an inverted reflection. It reversed itself. So if it's on the positive side, we call that a crest. If it's on the negative side, we call that a trough. So every time I sent a crest, it bounced back as a trough. Every time I send a trough, it bounces back as a crest. And so it's popping back and forth. Now, the reason that every time it bounces back and forth, the amplitude, again, the amplitude was a measure of how much energy it has, how far it's disturbed from that rest position. So when I sent it with a bigger amplitude, every time it bounces back and forth, we get a smaller and smaller amplitude until it disappears. That's because the energy is turning into sound and heat. You can hear the noise as it's scraping across the floor, and it's heating up the spring slightly. And so it's turning into other forms of energy. Again, the energy doesn't just disappear, it turns into a different form. So if I, again, send a single disturbance, a pulse, I'm going to send a crest pulse, it bounces back as a trough, a trough pulse bounces back as a crest. Now, the speed of the wave is determined by the medium. It doesn't matter what I try and do to it, the speed it takes to go back and forth is going to be the same amount of time every single time. That's not going to change unless I change the medium. So if I would grab this medium, now I stretch the spring out more, and so it's actually a different medium now than it was that I've changed the characteristic of the medium. And so now I have changed the speed. Notice that it's going much, much faster now as it's going back and forth. And so if I change the medium, I'm going to change the speed. And so anytime I want to change the speed, I have to change the medium. I can change to a different medium, or I can just change the characteristics of the medium we're in. For instance, when I talk, the medium is sound, a medium of sound is the air. And so the air temperature will change the medium. And so if it's a really hot day outside, the sound is going to travel differently than if it's cold outside. So that's just an interesting aside. So again, a transverse wave has crests and troughs and disturbs the medium at right angles to the direction of wave flow. We also have what's called a longitudinal wave. And a longitudinal wave disturbs the medium the same direction the wave flows. And so if the wave is going back and forth this way, I now have to disturb the medium the same way it goes, this way and that way. So if you'll notice there, I do that, and you see this little scrunched up part move back and forth. That scrunched up part is called a compression because the spring was compressed. And you're saying, well, that was fun, but can you make it if you move it the other way? And yes, I can. So if I pull this way, what moved was a stretched out part, not a scrunched up part. And so that stretched out part is called a rarefaction, which is a very fun word to say if you say it like you're mad. Rarefaction. And so everybody likes that word. Anyway, so if I have one crest and one trough makes one wavelength this way, one compression and one rarefaction make one wavelength that way. So crests and troughs go with transverse waves, and compressions and rarefactions go with longitudinal wave. Sound is a longitudinal wave. It sends compressional waves because your vocal cords vibrate the sound back and forth in that same direction that the wave travels. So that's these kind of waves. Now, there is a relationship between the speed was controlled by the medium of the wave, but there is a relationship, an inverse relationship between the frequency and the wavelength. Now, frequency is how fast I choose to make the wave. So I am in complete control of the frequency. The spring itself is in control of the speed. But you'll notice if I try and make a really slow wave, the wave is very big. If I try and vibrate this very quickly, what we get are very small waves. We get a lot of waves. So one wavelength in a transverse wave, again, is one crest plus one trough. And so one wavelength in a longitudinal wave is one compression plus one rarefaction. So if I'm making a lot of them, then the wavelength is going to be smaller. If I'm doing this real slowly, then the wave is going to be bigger. It's going to be longer in that stretching. This is a little bit more difficult to do in this particular thing, but this is all I have here at home, so you'll have to bear with me. So again, if I make what I made right there was called a standing wave. A standing wave is a wave with a regular repeating pattern. And so I was still making a transverse wave, I was still making crests and troughs there. But what happened was, as I sent a wave that way, it hit his hand and reflected back to me. And so the reflection going this way started messing with the reflections going that way. And so the two different disturbances start to mess with each other. When they interact like that, we call that interference. And there are two types of interference. We either have constructive interference or destructive interference. In constructive interference, a crest hits a crest or a trough hits a trough to make a bigger crest or a bigger trough. But when a crest hits a trough, then the crest is trying to pull it one way, the trough's trying to pull it the other way, it ends up getting smaller. That's going to be destructive interference. So destructive interference when opposite ones hit each other, constructive or when they both are happening. You don't see the standing wave when I first start to wiggle this. It only happens once it hits him, starts to reflect back, and the reflected ones and those are starting to mess with each other. So again, watch this carefully, it goes quickly. But you'll notice that pattern didn't start to actually develop until the waves hit him and came back, and so the ones coming this way and the ones coming that way are messing with each other, are interfering, either constructively or destructively. Now you probably noticed that there were some funky things that were happening in the wave when I made the standing wave. There were two parts in the middle that were just kind of pivoting. They weren't really moving this way or that way. The spring was just pivoting. And then there were other sections where it was moving a lot. The sections where it's moving a lot are called antinodes. There are no uncle nodes, just antinodes. So an antinode is the point where we're having the constructive interference, where a crest is hitting a crest to make a bigger crest, or a trough is hitting a trough to make a bigger trough. Where we have the nodes, that's the point of destructive interference, where a crest coming one way is hitting a trough coming another way, and they're canceling each other out, and so it pivots right there, but it doesn't continue to move the medium. So again, watch for this. We'll start off with just one antinode here. So if I find the right matching frequency, here I have nodes at both ends, but I just have an antinode in the middle. If I go to the next standing wave, right here, you look in the middle of the wave, in the middle there, it's kind of just pivoting, and we have an antinode here and an antinode over there. And we have nodes at the end. So now we have one whole wavelength, we have two antinodes, and we have three nodes. If I shake it faster, let's find the right one. We gotta find just the right matching speed. There we go. Now we have three antinodes and four nodes, so 1 1/2 wavelength. Now standing waves we can make both vertically too, so come up a little bit. It might be easier if you come down a little bit, but I'm going to try and make the waves this way.
I was going to ask you if you were going to swing rope.
So this is a lot quieter too. Bring that up just a little higher. Thank you. So here we have again our first standing wave, and our first standing wave is only half of a wavelength. So we have an antinode in the middle. It's either a crest or a trough, but we don't have a crest and a trough at any given moment. And at both ends, since we're clamping them down, the only thing that can form is a node there. So then if I go to the next standing wave, that would be right here. And so that pivot point in the middle here is the node, and I have an antinode here and another antinode over there. And so I have one whole wavelength here. And if I increase the energy, then the amplitude gets bigger, it gets taller, farther from the rest position, but I still only have one wavelength. So the wavelength didn't get any bigger. The height of the wave or the amplitude got bigger. If I add less energy, it's gonna get smaller, but it's still one wavelength because I'm still vibrating at the same frequency. If I go to the next frequency where I can make the next standing wave, and again, I have to find the right frequency. There we go. So now you can see there's a node here and a node there, and there's a node at each end. So we have 4 nodes and we have 3 antinodes. So here I have 1 1/2 wavelengths. So this is a standing wave. And then you can try and get to the point where I get 4. This one might be a little tricky. There we go. Kind of pretty, right? So there are also what are called torsional waves, and a torsional wave will go pivoting like this. And so here we have a torsional wave that's also a standing wave because you can still see the node right there and a node right there. So this is 1 1/2 wave. But a torsional wave is one that is twisting instead of going longitudinal or transverse. So that pretty much does it for waves. So hopefully there's a bunch of stuff you understand. I'll ask you a whole bunch of questions on this. You'll probably have to go back and watch this 3 or 4 times to get it right. I ruined my brand new slinky, but it's okay because hopefully you learned something. So, see ya.